Hello friends, we hope you are enjoying our featured videos. We are thankful for the warm response so far and look forward to your continued support. Today's topic is atmosphere and weather. One of the most fundamental aspects of meteorology. Here we will be breaking down different components of the atmosphere and their importance on weather patterns. So get ready to fly. Earth's atmosphere comprises multiple layers, with each of them having a specific role to play. Before we start getting into the layers of atmosphere, it is important to point out that our reference always starts from the ground, which is ground zero. From ground zero, extending up to approximately 13 kilometers high, is the troposphere, which subsumes the tropopause, the topmost layer of troposphere. This part of the atmosphere is the densest, and almost all weather related events happen at this level. Next up, the stratosphere. The stratosphere starts just above the tropopause and extends roughly to about 50 kilometers. The ozone layer, which absorbs and scatters the solar ultraviolet radiation, is part of stratosphere. Just above the stratosphere lies the mesosphere, and it extends roughly about 90 kilometers high. In one line, the mesosphere burns up most meteors and asteroids before they are able to reach the Earth's surface. Now, next is the thermosphere. The thermosphere extends to 500 kilometers. The aurora happens in this layer. Within this layer of the atmosphere, ultraviolet radiation causes photoionization or photodissociation of molecules, creating ions in the ionosphere. The ionosphere is defined as a layer of the Earth's atmosphere that is ionized by solar and cosmic radiation. It lies roughly 100 to 1000 km above the surface and includes parts of thermosphere and exosphere. Because of the high energy from the sun and from cosmic rays, air is ionized in the layer. It plays an important part in atmospheric electricity. It has practical importance because it influences radio propagation to distant places on the earth. And above all these layers lies the exosphere, which is the topmost layer of our Earth's atmosphere. It extends from the to roughly 3000 km and beyond. This is the layer where majority of the satellites are placed. The atmosphere is made up of air. So now let us discuss the state of air in these regions. We all know that as we move vertically up, the pressure and temperature of the air decreases. The ground has the highest pressure and temperature. As pressure and temperature reduces, the density of air also reduces. This implies density of air is highest near the ground and decreases as we move up. This is precisely the reason why air is the thinnest or rarefied at high altitudes. The variation of density and temperature with altitude is called stratification. The highest temperature occurs near the ground, and the temperature reduces rapidly in the troposphere. The temperature starts to increase in stratosphere with increasing altitude, because the ozone layer absorbs the greater part of the solar ultraviolet radiation. The ozone layer is an absorbing agent that protects life on Earth. Following this, the temperature reduces drastically in the mesosphere due to decreasing absorption of solar radiation by the very thin atmosphere and increasing cooling by CO2 radiative emission. The coldest temperature are experienced at the top of the mesosphere, where temperature reaches minus 90 degrees Celsius. After this, temperature increases in the thermosphere and exosphere since they are the outer layer of the atmosphere and are subjected to high solar radiation. The decrease in the temperature and density in troposphere and the thickness of the atmosphere, or in other words, presence of strong stratification, makes the troposphere a very interesting layer of atmosphere with huge implications for weather dynamics. The presence of stratification leads to unstable or stable motion within this layer, leading to interesting weather patterns and genesis of complex weather systems. For example, the air near the ground is denser, so as the ground heats up, the density decreases, allowing the air to rise, creating instability. This process is famously known as convective motions or convective instability. When you see the top of the thunderstorm flatten out into an annual cloud, it is usually because the unstable motions in the storm have died down. The global circulation can be described as the worldwide system of winds by which the necessary transport of heat from tropical to polar latitudes is accomplished. In each hemisphere, there are three cells: Hadley cell, Ferrel cell, and polar cell, in which air circulates through the entire depth of the troposphere. First, the Hadley cell, the largest cells extending from the equator to between 30 and 40 degrees north and south, are named Hadley cells after English meteorologist George Hadley. Within the Hadley cells, the trade winds blow towards the equator, then ascend near the equator as a broken line of thunderstorms, which forms the Intertropical Convergence Zone, in short, ITCZ zone. From the tops of these storms, the air flows towards higher latitudes, where it sinks to produce high pressure regions over the subtropical oceans and the world's hot deserts such as the Sahara Desert in North Africa. Next, the Ferrel cell. In the middle cells, which are known as the Ferrel cells, air converges at low altitudes to ascend along the boundaries between the cool polar air and the warm subtropical air that generally occurs between 60 and 70 degrees north and south. This often occurs around the latitude of the UK, which gives them unsettled weather. Finally, the polar cell. The smallest and weakest cells are the polar cells, which extends from mid-latitude to the poles. The air in these cells sinks at the poles due to colder temperature in polar regions and flows out towards the lower latitudes at the surface. Next, we move into one of the most important dynamic aspects called the jet stream. Jet streams are fast flowing, narrow, meandering air currents in the atmosphere of some planets, including Earth. On Earth, the main jet streams are located near the latitude of the tropopause and are westerly winds, flowing west to east. Their paths typically have a meandering shape. The strongest jet streams are the polar jets at 9 to 12 km above sea level, and the higher altitude and somewhat weaker subtropical jets at 10 to 16 km. Meteorologists use the location of some of the jet streams as an aid in weather forecasting. The main commercial relevance of the jet streams is in air travel, as flight time can be dramatically affected by either flying with the flow or against, which results in significant fuel and time cost savings for airlines. Often the airlines work to fly with the jet stream for this reason. Dynamic North Atlantic tracks are one example of how airlines and air traffic control work together to accommodate the jet stream and winds aloft that results in the maximum benefit for airlines and other users. There are many more interesting patterns in the troposphere, such as waves, cyclones, and much more. We leave these topics to be explored on your own, having given a basic background of atmosphere and weather. For the sake of brevity and relevance, we end our discussion with stratosphere. The stratosphere is the second major layer of Earth's atmosphere, just above the troposphere and below the mesosphere. The stratosphere is stratified in temperature with warmer layers higher and cooler layers closer to the Earth. This increases the temperature with altitude, is a result of the absorption of sun's ultraviolet radiation by the ozone layer. This is in contrast to the troposphere near the Earth's surface where temperature decreases with altitude. The border between the troposphere and stratosphere, the tropopause, marks where this temperature inversion begins. Bacterial life survives in the stratosphere, making it a part of biosphere. In 2001, dust was collected at a height of 41 kilometers in a high altitude balloon experiment and was found to contain bacterial material when examined later in the laboratory. The purpose of this video was to bring to your attention the role of atmosphere in governing the weather and its related dynamics. We hope you find this extremely useful and informative, and this would set the stage for young and budding meteorologists, astrophysicists, or space explorers. If you like this video, please do share this with your friends and family, subscribe to our channel, and hit the bell icon for instant notifications and more exciting updates. You can also express your views and suggestions in the comment section. Stay tuned for our next video. Until then, this is Parthanin Gadar signing off for MedConnect.